Hello everyone, I am Karan Mashru. Welcome to this video. In this video, we are going to look at the solution of the problem, that is AVL tree insertion. First of all, let us start by understanding the question. What does question say? Given an AVL tree and n values to be inserted in the tree, write a function to insert elements into the given AVL tree. So basically, we want to insert values in the AVL tree. Okay. The tree will be checked after each insertion. If it violates the properties of balanced binary search tree, an error message will be printed followed by the in-order traversal of the tree at that moment. If instead all insertions are successful, in-order traversal of the tree will be printed. Okay, so if let's say I want to insert three values, let's say I want to insert 5, then 1 and then 4. So first of all 5 will be inserted, my tree will look like this. Then 1 means it will be inserted, it will look like this. Then 4 will be inserted, so initially it will look like this. Then after some work it will finally look like this. Okay, so the in-order traversal of this balanced binary search tree or AVL tree will be 1 4 5. Okay, then if 7 values are to be inserted, it will become this. Okay, so we will look at it. And you don't need to read input or print anything. Complete the function insert to AVL, which takes the root of the tree and the value of the node to be inserted as input parameters and returns the root of the modified tree. So basically we are given this function. In this function the root of the AVL tree will be passed, and the data which we want to insert will be passed, and we will be inserting that value, modified that tree if required, and then finally return the modified root. Okay, the expected time complexity is log n and expected auxiliary space is height of the tree, and the constraints are given here. So now if we think about solving this problem, so basically see, we want to insert values in AVL tree. Okay, so first of all we need to understand some basics of AVL tree. What is an AVL tree? It is a balanced binary search tree. What is balanced binary search tree? First of all, let us cut this in two parts. So what is balanced and what is binary search tree? Binary search tree is a binary tree in which the value of the root or the value of any node is greater than value of the all nodes in left subtree. Okay, and value of the node is less than all nodes value in right subtree. Okay, so that is basically a binary search tree. Okay, so let's say this is 12, this is let's say 9, this is let's say 8, this is let's say 10, let's say this is 13. Okay, so this condition should hold true for all the nodes. So for example, 12 is greater than all the nodes values in the left subtree, and it is less than all the nodes in the right subtree. Similarly, 13 is the leaf node, so no need to check further. Now 9 is greater than all the nodes in the left subtree and less than all the nodes in the right subtree, and 8 and 10 are leaf nodes, so no need to check. So this is a binary search tree. Okay, now what is balanced binary search tree? See, if I give you this is a binary search tree. Okay, it is fulfilling this property, but this is not balanced binary search tree. Okay, what is the meaning of balanced binary search tree? It means that the balance factor of all the nodes should be either -1 or 0 or 1. Now what is balance factor? Balance factor is nothing but height of the left subtree minus height of the right subtree. Now this balance factor should be either -1 or 0 or 1 for all the nodes. If it is not from any of these values for even one node, then it is not balanced. Okay, so for example, what is the balance factor of this node? It is 0 because there is no left child, there is no right child. Similarly, balance factor here is 0. What is the balance factor of this node? Left child has height 1 and right child also has height 1, so the balance factor here is 0. Okay, what is the balance factor of this node? 0. What is the balance factor of this node? Height of the left subtree 1 and 2, height of the right subtree 1. Okay, so height means the longest path until the leaf. Okay, starting from that node. So this is 2 minus 1, so this is 1. So here all the nodes have balance factor from these three values only, so this is balanced. Here if I calculate the balance factor for this node, then height of left child is 1, 2 and 3, and there is no right child, so that is 0, so this is 3, so this is not balanced. Okay, similarly the balance factor here is 4, so this is not balanced. So what is balanced binary search tree or AVL tree? Where the balance factor of all the nodes is either -1, 0 or 1. Okay, now so if I want to do insertion in an AVL tree, what I will do is, first of all, I will insert the value as per the rules of binary search tree. Okay, and then I will balance any unbalanced node. So first of all, we'll simply insert the new value which we want to insert according to the rule of the binary search tree, and then if any node is unbalanced, we will balance it. So for example, let's take this example. So this is 12, this is 9, this is 8, this is 10, and this is 13, right? So what I will do, let's say I want to insert 11. Okay, so first of all, I'll start with the root node. If the value to be inserted is greater than the current node value which we are looking at, then that value will be in the right subtree according to the rules of the binary search tree. So we will go on the right subtree part. If the value to be inserted is less than the current node which we are looking at value, then we will go in the left subtree. If it is equal to, we will skip inserting it. Okay, we will not insert the same value. Let's say I want to insert 11. Now 11 is less than 12, so it will be in the left subtree of 12. So I'll come here. Now I'll compare 9 and 11. 11 is greater than 9, so it will be in the right subtree of 9. So I'll come here. Now 11 is greater than 10, so 10 will be in the right subtree of 11 will be in the right subtree of 10. There is no right subtree. So what I'll do, I'll insert 11 here. Is it a binary search tree? Yes. Is it a balanced binary search tree? We need to check. So how will we check the balance, whether it is balanced binary search tree or not? See, after every insertion, we are balancing it. Okay, so every insertion will be in two parts. One, insert the value and then balance the tree. Okay, so after every insertion, the tree will be balanced binary search tree or AVL tree. Okay, so whenever we insert a new value, we only need to check whether it is imbalanced with respect to that node or any of its ancestor. Because when I insert 11 here, height of this node will change, height of this node will change, height of this node will change, and height of this node will change. Height of its ancestor only will change. So those nodes can only become imbalanced. Okay, are you getting my point? For example, here there is one subtree T1 and here there is one subtree T2. Then T1 and T2, in that any node cannot get imbalanced. Okay, because before this step the tree was balanced. After every insertion we are balancing the tree, right? So now we inserted this, right? So now if I calculate the balance factor of 11, it will be 0. The balance factor of 10 is 0 minus 1, that is -1, that is also balanced. The balance factor of 9 is 1, height of left subtree, and 2, height of right subtree, that is -1, that is also balanced. The balance factor of 12 is 1, 2, 3, height of the left subtree is 3, and 1, height of the right subtree is 1. So 3 minus 1, that is 2. So this is not balanced by balanced binary search tree. This is not balanced with respect to this. Okay, now what we need to do, now let's have a look at this. But the first step is clear. How will we insert it? We will keep going on left or right with respect to the property of the binary search tree, and whenever we reach a leaf node, we will insert on the left child or right child respectively as per the value. Then we will keep coming back, and for all its ancestor we'll check the balancing factor, and if they are not balanced, we will need to do some work. Now let's look at it. So now after inserting a value, let's say the tree became unbalanced. Okay, so let's say it became unbalanced with respect to node X. Okay, in all the 4 cases. Here X, Y and Z are nodes, and T1, T2, T3, T4 are subtrees. Okay, so now this is the first case when, let's say X is the first unbalanced node, when after inserting the value, when we were checking their ancestors one by one during backtracking, X is the node which is unbalanced. Okay, so let's say the value which we inserted is in the left child of the left subtree of X. Okay, so what is the left subtree of X? It is starting from Y. The value which we inserted is in the left child of Y. Okay, so it is somewhere in this part. Okay, so this is called left case. Okay, Similarly here, let's say the value which we inserted is in the right child, in the right subtree of the left subtree of x. Okay, so the left subtree of x starts from y, and in its right subtree we inserted the value. So this is called left right case. Okay, similarly here this is called right right case. Let's say the value which we inserted is in this part. Okay, and this is called right left case. Okay, now let's say the tree is imbalanced, okay, from the point of view of x. Okay, so now what we will do here is, here we need to do a right rotation. Here we need to do a right rotation on x. Okay, so what basically right rotation on x means, we will this part we will rotate it on the right. So x will come on the right and y will come on the top. So y will come here, x will come here, t1 will come here, z will come here, t3 will come here, sorry, this is a subtree, and t4 will come here. Now understand one thing. So x is the right child of y. Okay, now right child of y was t2. So now where will we place it? See, understand one thing, t2 is less than x but it is greater than y. So T2 will come on the right of y because it is greater than y, but it will come on the left of x because it is less than x. Also, the left child of x is now empty. So what I can do is I can place T2 here. Okay, and this will now become balanced. Okay, why? See, here initially, let's say it was inserted somewhere here. Okay, let's say my let's take a simple example. Okay, so let's say the value there is a one here, it is x1, here it is x2. Now these are nodes. Okay, these are not subtree, and this is x3. Okay, and let's say here there is no value, here there is no value, and here also initially there was no value. Okay, so if I look at this, what is the balance factor of this? 2 minus 1, 1. What is the balance factor of this? 0. What is the balance factor of this? 0. Balance factor of this? 0. Balance factor of this? 0. So everything is balanced. Suppose I enter x3 here. Okay, x3 is taken, no. Okay, suppose I enter x3 here. Now what is the balance factor of this? 0. Balance factor of this? 1. Balance factor of this? 1. 2 minus 1, 1. Balance factor of this? 3 minus 1, 2. So it is imbalanced from this point of view. So if I right rotate it, what will happen here if I draw it here? So y will come here, x will come here, x1 will come here, then x2, that is the right child of y, will be the left child of x, z will come here, and x3 will come here. Now is it balanced? Look, everything is balanced. This balance factor is 0, this is 0, this is 0, this balance factor is 1, this balance factor is 0. So it is balanced. So what we do is we do the right rotation on x. Okay, don't worry about the implementation, we will have a look at that. Now this is the left right case. Okay, where the new node inserted is somewhere here. Okay, in this subtree, and due to that it became imbalanced. Okay, now we will not be taking such kind of examples for every case. You can take an example where the tree was initially balanced, and after inserting the value in the right child of the left subtree of x, it became imbalanced from the point of view of x. Such example you need to take. Okay, and then work out on it. Okay, so here what we will do, first of all, here we will do left rotation on y, and then we will do right rotation on x. Okay, so left rotation on y means catch y and rotate it left. Okay, so what will happen? X will come here, then z will come here, t1 will remain here only, right? Then z will come here, t2. Okay, or z will come here. Now y will be the left child of z. Okay, and t3 t4 will come here, t4 will come here. Okay, now t3 is the left child of z, it will become the right child of y. Okay, similarly how t2 became the left child of x here, t3 will become the right child of y, and t2 will remain here only. Okay, So this will happen, and after this you will do right rotation on X. Okay, so Z will come on the top, then X will come on the right, and T1 will come here. Okay, so T1 came here, X, T1 and Z are done. Now T4, that is the right child of Z, will be the left child of X. So T4 will come here, Y will come here, and T2 will come here, and T3 will come here. Okay, so this is the left rotation on Y and then the right rotation on X, and this will be a balanced AVL, balanced binary search tree or an AVL tree. Now let me rub this part and then we'll look at these two cases. Okay, so now let's look at these two cases. So this is the right case where the new node inserted is somewhere in the right subtree, right child of the right subtree of the right child of X, and X is the imbalanced node. Okay, first imbalanced node starting from the leaf node. Okay, so now what we will do, this is right case, so we will simply do a left rotation on X. Okay, so we will catch it and rotate it left. So Y will come on the top, X will come in the left child of Y, T1 will remain the left child of X. Now T2 will become the right child of X. Okay, then Z will remain here only, this will become T3 and this will become T4, and this will be a balanced one. Okay, now let's look at the fourth case. This is the right left case. So what we will do here, so here the new node is inserted in the left subtree of the right child of X, and X is the imbalanced node. Okay, so here what we will do, first of all we will do a right rotation on Y, and then we will do a left rotation on X. Okay, so let's do a right rotation on Y. So Y will be shifted right, Z will come on the top. Okay, so what I will get, this is X, and Y will be shifted right. So Z will come here, Y will come here, right? T2 will come here. Then what is the right child of Z? It is T4, right? Right child of Z will be the left child of Y. So this will become T4. Then T3 will remain here only, and T1 will remain here only. Okay, now we will do left rotation on X. So X will be rotated left. Okay, so what will happen, let me draw it here. Z will come on the top, X will come here, T1 subtree will remain here only, T3 subtree will come here, then Y will come here, and T4 will come here, and T2 will come here, and this will be balanced. Okay, so this is what we are going to do. Now let's look at its actual implementation. So now if we look at the actual implementation, so see here, first of all, this is the function which you need to complete. This is the node which root of the binary search tree or the AVL tree, and this is the data which we want to insert. If node is null, means this is the first value which we need to insert, then node is equals to new node and data. So this is a constructor function which is defined in the driver code, where you pass the data. So a node will be defined, its height will be defined as 1, and left and right subtree will be given 0, null pointers. Okay, and then we will return this node only, because this is the new modified head of the or root of the AVL tree. Now if the data is to be inserted is greater than current node data, then we will insert it on the right subtree. So node right is equals to insert to AVL tree. I'll recursively call this function node right and pass the data. Now understand one thing, we are from this function we will be passing the modified root or modified root node of the AVL tree. Okay, so at every step, see, if I am inserting in the right subtree, then that right subtree's root node, okay, whatever that it may be modified, so I want to get it back into this pointer only. So I am writing node right is equals to insert this. Okay, because this will also be returning pointer to the root of the right subtree of the current node. Okay, then else if data is less than the current node data, then recursively call the left subtree. Otherwise, if it is same, then simply pass the node. Okay, if that node data and the new data which we want to insert is same, then simply call insert it. Okay, so finally what will happen is we will recursively go below the tree according to the rules of the binary search tree, and at some point of time we will reach a null node. Okay, this condition will occur either when we will reach the root node of a binary leaf node of a binary search tree and then null child, or when initially the tree is empty. So when we will reach the leaf child, we will make a new node and return it. Okay, so after completing this process, the height of the current node will be updated. It will be 1 plus max of height of left child or height of right child. Okay, we will update its height also. Then we will call for the balance of the current node. So now this is to insert the node. Now during backtracking, we will update the height and check for the balance of each node. Okay, so what is the balance, how it is checked? So get balance is, if node is null, return 0, otherwise return height of left subtree minus height of right subtree. That is the balance factor. Okay, and what is the height function? If n is null, return 0, otherwise return the height parameter from that node. Okay, so after getting the balance factor, if the balance factor is greater than 1 and if the data is less than the node left data, now understand one thing. If the balance factor is greater than 1, see, if the balance factor is either -1 or 0 or 1, then the tree is balanced from that node point of view. If it is not none of this, then it is imbalanced. So balance factor can be either greater than 1 or balance factor can be either less than -1 for a node when it is imbalanced. Now what is balance factor? Balance factor is height of the left subtree minus height of the right subtree. So if it is greater than 1, it means height of the left subtree is greater than height of the right subtree. It means the new node which was inserted is inserted in the left subtree only, because before inserting that node my tree was balanced, because after every insertion I am balancing my tree. So if the balance factor of a particular node is greater than 1, it means height of the left subtree is greater than height of the right subtree and the new node is inserted in the left subtree. Okay, so now there can be two cases. Let's say this is x, this is y. Now it can be inserted on this part or on this part. If it is inserted here, it will become left case. If you remember, if it is inserted here, it will become left right case. Now when it will be inserted here, when the value of the node to be inserted, the value of the new data value which is to be inserted is less than the left child value of the current node which is imbalanced. Okay, this balance factor is greater than 1. So if the new value to be inserted is less than y, then it will be inserted here, it will be left case. If it is greater than y, it will be left right case. Okay, and the balance factor is greater than 1. So if balance factor is greater than 1 and data to be inserted is less than node left data, so this is my node, this is my node left, that is the left child. If the data inserted is less than this, it will be inserted here, and if balance factor is greater than 1, it is left case. In left case, what I do right rotation on the node, on this node. Okay, is this much clear? Similarly, if balance factor is less than -1 and data is greater than node right data, then do left rotation on node. This will basically give you right case. Okay, you can draw and have a look. If balance factor is greater than 1 and data is greater than node left data, okay, this is node left. If balance factor is greater than 1 and new data is to be inserted is greater than this, then it will be inserted here, it will be left right case. So first of all, I will do left rotation on the left subtree left child and store that new modified root of the left child here, and then I will do right rotation on the current node, and then I will return the modified node. If balance factor, this is the fourth case, the right left case, you can draw and check it. Okay, and finally we will return the let's say it is none of these cases, so tree is balanced. So if it is none of these cases, I will return the node simply. Now let's look at these left and right rotation functions. So let's look at the left rotation function. So see, basically x is the root node, okay, which is imbalanced. Okay, so let me write down with respect to this so we can understand better. Okay, now y is the right child of left. Okay, so y is the right child of left and t2 is the left child of y. T2 is the left child of y. T2 means that's a subtree. Okay, and then they have done nothing. Okay, so basically see, here they are doing a left rotation on X. Okay, so let's say this is T3 and let's say this is T4. If I do left rotation on X, my Y will come on the top. Okay, now Y will come on the top, X will come here, T4 will come here, okay, T3 will come here, and T2 will come here. Okay, now tell me what are the things that have changed. X became the left child of Y, Y's right child is T3, so T3 is not changed. T4 is the left child of X, T4 is not changed. T2, which was the left child of Y, now became the right child of X. Okay, so T2 has changed. That's why they have taken only these values. X is the current node, Y is the right child, and T2 is the left part of Y. Why I have taken a pointer to that? Because now it will become the right child of X. Look, Y left is equals to X. The left of Y will now become X. And that's why I have stored the Y left before only, so that I do not miss it. And the right child of X will now become T2. Right child of X will now become T2. And the height of which subtrees will be modified. Okay, so the rotation is complete, but we need to modify the height. Will the height of T3, any node of T3 will be updated? No. Will the height of any node of T2 will be updated? No. Will the height of T4, any nodes in T4 will be updated? No. Height of X will be updated, yes, because now it has T2 as a child, and height of Y will be updated because now it has X and T4 as a child, okay, in its subtree. So X height will be 1 plus max of left and right, and Y height will be 1 plus max of left and right. And then finally we will return Y because this is the new root of this subtree. Okay, and similarly you can have a look at the right rotation by taking one example. What will be the time complexity? See, first of all, we are doing insertion. How much time it will take? It will take log n time. Why? Because it is balanced binary search tree. So if there are n nodes, the height can be at max log n. Okay, and in binary search tree, at each step we either go left or right, and then we either go left or right, and then when we reach the leaf node, we insert the respective value. Okay, so for inserting it will be log n. Plus, during backtracking, we check whether it is balanced or not. For checking whether it is balanced or not, we calculate its height. Now, for each node, we update its height as we go up. So, it takes constant amount of time. And rotation also takes constant amount of time. Because if any node is not balanced, there are at max 2 rotations required. Okay, so this is the log n time which we require to traverse below, and then again during the backtracking. Okay, what would be the auxiliary space? This will also be equal to log n, or you can say big O of height of tree. Why? Because we will be calling the recursive functions will be so those recursive functions will require a stack which will require this much space, and also the new values which we are inserting will require this much space. Okay, so this will be the auxiliary space and this will be the time complexity. Now let's submit this code. Let's submit it. So we have solved this question successfully. I hope you have understood this solution completely. Thank you.